Last week we saw how we can use polymorphism in tandem with type classes to provide ourselves with more generic and more powerful functions. This week we're going to take that a little bit further by understanding the concept of higher order functions. To motivate this, let's start with our QuickSort example. If you remember from last week, I said that QuickSort can be made to be much more concise, because really to understand this definition we need to also understand these two. So while QuickSort is very short here, this is a bit more cumbersome as a definition overall. But if we look at these two functions, they're extremely similar. They have the same type signature, they have the same base case, they pattern match on the same input, and they have a very similar logical test. All they do is they check that value is either less than or greater than, keep the values that are, and lose the ones that aren't. So they keep values that are there, that meet the condition, and they lose the values that don't. They filter the list. They filter the list based on a logical condition. And that's the function we're going to be looking at today. So if we have a wee look in terminal at the type of filter, just to get an idea for it, filter has a weird type signature, or at least a type signature that we haven't seen so far. So filter has this bit at the start. After this, it just takes a list and returns a list as output. But what does this mean at the start? Well, when you see something with brackets around it like this, with an arrow in the middle, we've seen tuple types and they're a little bit different, they just have pairs of items, but this actually has a function arrow in the middle. So what this means is this is a higher order function. This is a function which takes another function as an argument, and that's something that's integral to working with Haskell. Higher order functions are crucial to getting a benefit out of Haskell and using it as it's intended to. They are crucial. So it's very important that you understand this. So higher order functions are ones which take functions as arguments. And indeed you can do this in Java. It's quite difficult. It's a bit more complex and a bit less intuitive. It also relies on, not only does it take the idea of higher order functions from Haskell, but to implement it normally you would need a lambda function, which is another idea that's taken from Haskell or functional programming. So Java needs two ideas from Haskell to implement one idea from Haskell, whereas Haskell just goes out of the box and does it. But anyway, I digress. So what is filter? Filter is a function which takes a logical condition, applies it to each element of the list, and only keeps those elements if it meets that condition, i.e. it returns true. If it returns false, the element gets removed from the list. And that's exactly what we were doing up here. So let's compare it. Let's try less than. And we'll run this on say 5, and we'll just give it the numbers 1 to 10, a simple list to start with. And if this works properly, we should get the results of 1, 2, 3, 4 as a list. And indeed we do. But we can do the same thing with filter. So filter, and we need to give it a function. Let's worry about that in just a second. And we'll give it list 1 to 10. Now, we could define a function from A to Boolean, which takes a value of 5 as a hard-coded value and applies the less than operator to it. We could if we were so inclined. What I'm going to do is I'm going to move into the brackets first. I'm going to hit like that. Now, that may or may not make sense to you. What we're doing there is something called partial application. But really, what you should see this as is a function that checks for less than 5, another value to see if it's less than 5. We'll have a look at that in a second, but for the moment, let's hit enter and see if it does the same thing. So, we see that filter can do exactly the same thing as less than, but we don't need a big definition of filter because filter is already built into the Haskell infrastructure. But as I said, let's have a look at this less than, because this is another idea that's quite important in Haskell. If we look at the type of less than, we see that it takes two arguments of type A, which are part of the orderable type class. That makes sense. We know that that's a part of the definition of orderable. But how did this work? Well, this is something called partial application. And what that means is, in Haskell, when you have a function that takes more than one argument, you can give it one or more of those arguments, and as long as you don't supply every one of those arguments, Haskell will actually return a function for you. So we're getting through these ideas quickly, but in Haskell, you can pass functions as arguments. You can also return functions as outputs. So functions are the ways and means in which you do things, but they can also be the input and output of what you're working with. So functions are everywhere in Haskell. But really, if we have a look, stop using capital T, and I put less than 5, you can see that the function becomes A to Boolean, and that's exactly what filter was looking for. We can say that's orderable. Now it's part of the numeric type class of A. That's because I gave it a number, so Haskell has to infer that the other side should be a number, because it wouldn't make sense to say it is true less than 5, So what we've done here is we've supplied this first A, and Haskell has returned a function from A to Boolean. So that's the idea of partial application. We'll see this more and more as we go through. This is how you can manipulate functions to get the shape of output that you're really looking for, or the shape of a function that you want. Anyway, so we've seen that filter can be used to replace less than. It can also be used to replace more than. So let's see if we can make QuickSort a little bit more concise. So if I just go in here, and I replace less than with filter, and now I know that I need to supply a function. And if I want to get rid of the things that are less than p, I can just replace it with that. And now Haskell just goes, oh, okay, filter, that means we remove the elements that don't meet this condition. So take everything out of x's that is less than p, for whatever p happens to be at runtime. And of course, over here, I can do the same thing. And over here, I want to say things that are greater than or equal to p. So anything that's bigger or equal to p, that's on the right-hand side of the pivot element, and we can quicksort like that. So let's save, we'll reload, and let's call quicksort, and I'll just give it a random list. We'll give it 0 as the smallest element, mash the keys just so that it actually has to look through some stuff. We'll leave that 3000 as the biggest element, and check that it works. So there you go. Now I have an incredibly concise version of QuickSort, and I don't need these anymore. So now, because of the way that Haskell works, we're able to use polymorphism to have an incredibly generic QuickSort algorithm. So as long as it's orderable, we can apply this to any element or any type that can be ordered. Any type that has a definition of less than or greater than can be applied to this function. And we have a 2-line definition of QuickSort, really. And I think that's incredible. You're welcome to disagree, but this is the power of Haskell's abstraction. We don't need to care about how the computer has to sort through the elements. We don't have to care about how filter says, oh, now current pivot is equal to this value 5, and then it checks everything at 5 against every other value and sorts them out into 2 partitions. We really don't need to care about that. We just tell the computer, you should recurse and you should filter out these elements. That's all we tell it. And this is the power of a declarative programming language versus an imperative one. In C or Java, I don't know how many lines, it's something like 40, maybe 60 lines to implement QuickSort. For those of you that tackled the implementation in CS207, you'll probably look at this and see it as much, much, much more concise than your definition. But this is the power of abstraction. Now, when you look at these things, I don't want you to get bogged down into thinking, how does this work part by part, as in, how does filter check each element and how does it remove the elements? I want you just to read this as, okay, we're filtering out elements less than p and we quicksort on that list. And then on the other hand, we filter out elements that are not greater than or equal to p and we quicksort over those elements. But that's everything for today. I hope you found this useful. We'll be doing more work on higher order functions. We'll see some other higher order functions this week. If you have any questions about anything I've covered here today, please do let me know. Thanks.